Welcome back to our pre-AP notes. We're going to be looking at how to draw diagrams or pictures for covalent compounds. For covalent compounds, we're going to draw Lewis structures, named after Gilbert Lewis, who came up with this idea of drawing things in this manner for covalent compounds. And it shows the shared pairs of electrons that we know covalent compounds do as lines, and then lone pairs, unshared electrons, as dots. Again, all the directions you're going to need are here. Yes, it is quite a few steps, but once you get used to the steps, you will go very quickly through a lot of them. And there's even compounds where you don't even get to some of these last steps. But the easiest thing probably to get this understood is to go to some examples. So we're going to do some examples of drawing covalent compounds using Lewis structures. I start with the formula, so let's start with carbon tetrachloride. And the first thing I do is count up all the valence electrons. Carbon has 4 valence electrons. That's why it's in group 4A. Each chlorine has 7 valence electrons, and I say each, I have 4 of them, so I need to add that all up. That's 32. Now, every single electron in my drawing is going to be paired up, so let's make some pairs. In my drawing, I need to show a total of 16 pairs for my drawing to even be in the ballpark of correct. Now I'm actually ready to draw, and I look at the structure and I say, which atom's going to be in the middle? Well, nature loves symmetry. Take AP chemistry, we'll learn why. But nature loves symmetry, and so we're going to put the carbon in the middle and draw 4 chlorines around it. Now I'm drawing those chlorines in, if you will, a T-shaped or plus sign shape. That is not their actual shape in real life. We will get to later how to actually show the shape in real life. All right? But I'm going to start by connecting them with bonds. Hopefully so far that makes sense. That carbon is bonded to that chlorine, bonded to that chlorine, bonded to that chlorine, bonded to that chlorine. That has already used up 4 of these 16 pairs. Now we're going to do lone pairs. And to do lone pairs, we start by going on the outside atoms, giving each outside atom an octet except for hydrogen. I'll show that as an example later. This chlorine already has 1 pair, 2 electrons. So it needs 3 more pairs. Now that chlorine has an octet. Let's move to this chlorine. Identical situation. So I'm going to draw 3 lone pairs. It has an octet. Over here, 3 lone pairs. It has an octet. Over here, 3 lone pairs. It has an octet. So now I'm showing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pairs of electrons around carbon tetrachloride. That actually means I am finished. Now I want to end by checking that the carbon has an octet as well. It has, if we count what's sticking onto the carbon, it has 4 pairs, 4 bonded pairs, but 4 pairs nevertheless. The lines count as 2 electrons. So it also has an octet. So this drawing is good. Everything has an octet. And that is our Lewis diagram for carbon tetrachloride. Now in real life, it would not look this way. 3-dimensionally, it would look a little bit different. I look at the central atom and I ask how many bonds are on the central atom. 4 bonds are on the central atom. Do I have any lone pairs on the central atom? The answer is no. 0 lone pairs. Okay? That gets me a numerical series, 4, 0, that then I can take to the chart on the back of the notes, this chart, and looking up 4 central pairs, 0 of them being lone pairs, I get 1 combination, and 1 combination only. That tells me the shape is tetrahedral. In real life, it would look this way. So in my work, I would want to say that the e.g., the electron geometry, if I count all the electrons around the central atom, is tetrahedral. The mg, that is, if I ignore the lone pairs and only look at the bonds, it is still identical because there were no lone pairs, so it's also tetrahedral. Okay. The polarization, is it polar or nonpolar? Okay, well, symmetrical molecules are nonpolar and asymmetrical molecules are polar. So this, even though it is drawn incorrectly in terms of three-dimensional, this is definitely going to be symmetrical. If you look at the picture that it would be in real life, which looks this way, it is still going to be tetrahedral. If you don't believe me, please ask. Well, sorry, it's still going to be nonpolar. If you don't believe me that these cancel each other, if these are symmetrical, please come to class and look at my little three-dimensional models that I have of these shapes, and you would see that yes, they do cancel each other out. They do match up. So it is nonpolar. And then finally, let's finish it off with hybridization. What orbitals would it take to have 3 pairs held? Remember, we showed orbitals as boxes with arrows inside. One box can hold 2 arrows at most. Well, I need to show 2, 4, 6, 8 electrons. So it would take one s, and only have one s orbital in any given energy level. So I need to go to p, and it would take 3 p's to hold a total of 4. One pair can be held in the s, 3 pairs can be held in the p, so its hybridization is sp3. So in this picture here, okay, I can't say this is s and these 3 are p. Each of these bonds are a mix now of 1s and 3 p's, all mixed up. That's how I can hold 4 pairs of electrons around carbon. All right. Now that, believe it or not, is a rather simple illustration, example of Lewis structures, but the other ones aren't necessarily any more difficult. They just take longer to work through. Let's look at another common and fairly simple picture. Let's do water. Water, we know, is a covalent compound, H2O. Each hydrogen is worth 1. The oxygen is worth 6. That's a total of 8. I'm going to divide by 2. That's 4 pairs I need to show in my picture. Oxygen in the middle, hydrogens on each end. Okay, so I've done my central bonds. I'm ready to do lone pairs on the outside, except hydrogen never does any lone pairs. Hydrogen can only have an s orbital. It's full when it has a pair already, and that bond is already a pair counting for that hydrogen. So hydrogens cannot have any lone pairs. Well, I need to show 2 lone pairs because I only am showing 2 bonds, so 4 minus 2. I still need to show 2 lone pairs. If I can't put them on the outside anymore, I go back to the inside. So we start on the inside with the bonds, we go to the outside with the lone pairs, and we come back inside with any leftover lone pairs. So oxygen is going to have 2 lone pairs. And the Lewis structure for water is going to look something like that. Okay. Let's look at what that would be in real life. I have a total of 4 pairs around the oxygen, but 2 of them are lone pairs. So now we're going to go to our chart, and we're going to find the combination of 4 lone pairs, 4 bonds, 4 pairs total, 2 lone pairs. It's tetrahedral for electron geometry, but for molecular geometry we call it angular or bent. Notice how those lone pairs are on one side and the bonds are on the other. That means it is not going to be a straight molecule, which is why we call it angular or bent. So over here, for the electron geometry, we would say tetrahedral because of the 4. When we look at the molecular geometry, just the number of bonds, it's going to be bent or angular. I'll take either one. Okay, polarization. Well, that looks symmetrical, but we're wanting to look off the picture of real life, three-dimensionally. Three-dimensionally, that does not have symmetry because atoms cannot be symmetrical with lone pairs. And you can't draw a line down through the middle like it looks like here. Again, check my model in the classroom. You'll see why. So this is polar. It is not symmetrical. Hybridization. What would it take to hold 4 pairs of electrons? Well, it would take 1s and 3p orbitals to do that. So there's our hybridization. All right? And again, so far these have been fairly simple. Okay. I want to introduce another idea to you now as we're doing our Lewis drawings. And it's really well illustrated with carbon dioxide. We start out the same. Carbon's worth 4, each oxygen's worth 6. That's a total of, can you do it in your head? Hopefully, 16. Divide that by 2, I'm going to show 8 pairs. Carbon in the middle, oxygen on the outsides, lone pairs on the oxygens, and I have 8 and I'm showing 8. So I'm done? Well, I'm not done. Here's the issue. Each oxygen has an octet. Octet there, octet there. Carbon doesn't have an octet. Right now it only has 2 pairs, or 4 total. So what's going to happen is this oxygen is going to say, hey, no worries. I have all these lone pairs. Let's share another lone pair. Oxygen still has an octet, 2, 4, 6, 8, but carbon now has 2, 4, 6. It's getting closer to an octet. Well, if it works well on that side, let's do it on this side as well. So now we have 2, 4, 6, 8 there. So now carbon has an octet and each oxygen has an octet. And I am showing around the central atom, this counts as 2 areas of electrons. One area here, one area here. We count multiple bonds, double bonds, triple bonds as one area. So 2 areas, and of those areas I have 0 lone pairs. Go to the chart and you'll find your electron geometry is linear. This would be a straight molecule. Your molecular geometry is also linear. Again, a straight molecule. Because it is symmetrical, it's going to be nonpolar. And what would it take to hold, now be careful about this, okay. What would it take to hold 2 areas of electrons? 1s and 1p. So carbon has an area of double bond here and an area of double bond there. That's a hybridization of sp. Take AP chemistry and we'll learn that these double bonds are a sigma bond and a pi bond, and only sigma bonds count towards hybridization. All right, but easy enough just to think how many areas of electrons does it have around it, and that works as well. All right, so that's what to do if you need a multiple bond. How did I know I needed a multiple bond? Because my central atom did not have an octet, and the elements carbon, nitrogen, oxygen, phosphorus, and sulfur will always, those 5 elements will always get an octet, so you better show that they have an octet in the middle. If it's not one of those elements, then just leave it alone. It's okay without an octet. And you can have more than an octet, but these elements must have a minimum of an octet around the central atom. Okay, I want to illustrate another example with a multiple bond. Hydrocyanic acid. Hydrogen's worth 1, carbon's worth 4, nitrogen's worth 5. So I need to show 5 pairs. What's in the middle? Well, we actually have quite a bit of choice, so here's our rule. The least electronegative. You're like, oh man, I don't know the electronegativity numbers. You never had me memorize them. Why do I need to know the electronegativity numbers? You don't. Okay, so quit complaining. In the periodic table, which actually looks a little more like that, we know fluorine to be the most electronegative. So the element farthest from fluorine will be the one in the middle. That makes carbon, the one in the middle. Nitrogen on one side, hydrogen on the other side. I've showed 2 of my 5 pairs. Let's start our octets. Nitrogen gets an octet. Hydrogen does not get an octet. I'm showing 1, 2, 3, 4, 5 pairs. I'm done. Uh-oh, carbon does not have an octet. Well, let's fix that. Let's double bond between the carbon and the nitrogen. Nitrogen still has 2, 4, 6, 8, but carbon has 2, 4, 6. Uh-oh, it doesn't have an octet yet. Well, let's fix that. We can't do any multiple bonding with hydrogen. It's done, it's full. So I'm going to continue working with the nitrogen. Nitrogen still has 2, 4, 6, 8, and now carbon has 2, 4, 6, 8, and hydrogen has the 2 that fills it up. That is what we would want to see for a Lewis diagram, a triple bond. Again, that's 2 areas of electrons around carbon, 0 lone pairs, and so we're going to have an electron geometry that is, again, linear, a molecular geometry that is linear. Polarization, well, hydrogen cannot balance out a nitrogen, so it is going to be polar. And hybridization, with 2 regions, it's going to need an sp. All right? So that's how to handle it when it has multiple bonds. And again, I'm looking for those elements of carbon, nitrogen, oxygen, phosphorus, and sulfur for the ones that are going to do the multiple bonds. If they're in the middle, be sure they have at least an octet. If they have more than an octet, that's fine. You're done. Move on. But if they do not have at minimum an octet, you need to be sure that happens by making multiple bonds. Okay, one last thing I want to illustrate. Actually, this one's going to involve 2 things at once. They could be separate. For the sake of an easy example, I'm doing both at the same time. That's a 3. NO3 minus. Okay. First thing I want to illustrate is what in the world are we going to do with the charge? Well, that's easy enough. Nitrogen is worth 5. Each oxygen is worth 6. And what's it take to have a negative charge? It takes an extra electron. Remember, negatives means we've added electrons, and we're counting electrons here. So this is a total of 24. Please don't mess up. If this is a positive here, that means you would subtract 1 here because you have less electrons. And negatives here mean you add because you have more electrons. If that was a negative 2, I would add 2. If that was a negative 3, I would add 3, so on and so forth. Okay. We're going to show 12 pairs in this. Nitrogen, 3 oxygens, put in my lone pairs, and bracket with charge. Why bracket with charge? Because I had a charge there. So I'm going to bracket and put the charge on the outside. That's the 2 things we do to handle a charge. Is we add or subtract as we're counting up our electrons, and we put a charge sign with the brackets around the whole picture showing the charge on the outside. If I didn't have that charge there, I would not have brackets here. Anytime I have a charge here, I do have brackets here. Now I'm looking at this picture and I'm going to double check it. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. This oxygen here has 2, 4, 6, 8. Nitrogen has 2, 4, 6. Well, it's obviously going to need a multiple bond. Where should I multiple bond? Here, here, or here? Good answer. We have a choice. We could multiple bond with the top oxygen, and now nitrogen is good with 2, 4, 6, 8. We could multiple bond with the one on the left. Notice how it has less lone pair, so it still has 2, 4, 6, 8. Notice I'm still putting the brackets, I'm still putting the charge. That's another option. So we have the option of it double bonding at the top. We have the option of it double bonding on the left side. Guess what we also have? The option of it double bonding on the right side. Still using the bracket and the charge because I had the charge there. So all three are possible. Which one do I show? Which one do I pick? How do I know which one to put on my paper? You put all three on your paper. When there's more than one picture that could represent the compound, you need to show all the possibilities. They're called resonance structures, and you're going to draw double-sided arrows between them to show the resonance structures. So I'm showing more than one picture, and I'm showing double-sided arrows, not because it had a charge, but because there was a choice as to what to multiple bond with in the diagram. So this example is showing two things at once, how to handle a charge and how to handle resonance structures. You do need to squeeze into the box on your homework all the pictures if more than one picture is a possibility. Now that'll only be the case if you have a multiple bond. If they were all single bonds, I would guarantee not have resonance, and only if there is a choice of where to put the multiple bond do I have a chance of resonance. Otherwise, like we had with hydrocyanic acid, there was no choice. I couldn't multiple bond with hydrogen ever, so it had to go there. There was no choice. So I only needed one structure. Okay. Let's finish this example off. For its electron geometry and its molecular geometry. Nitrogen has 3 areas of electrons around it. So its EG of 3 tells me it's trigonal planar. It's a triangle shape and it's going to be flat. Its molecular geometry is also just a 3. There is no lone pairs. So it's also trigonal planar. This is a 3-0 combination. On your chart, you'd look up 3-0 and you'd get those. All right. Your polarization, okay, a double bond cannot balance out single bonds, no matter how we try. So it is polar because it is asymmetrical. And hybridization, what's it take to hold 3 areas of electrons? 1 s and 2 p's. Total of 3 there. All right, so that really is all there is to drawing Lewis structures for covalent compounds. Again, what I just went through in all those examples are these 10 steps, and it probably did not feel like 10 steps as we got going because a lot of the steps are very quick, and in some cases we were able to skip steps 8, 9, and 10. So it really is, you're going to do steps 1 through 7 for everything, and then 8, 9, and 10 as they're necessary. So be sure you read the if statements there very carefully. All right, good luck. The only way to get really good at dot diagrams and Lewis structures is practice, practice, and more practice. And that's why you have about 18 dot diagrams to draw and 24 Lewis structures to draw so that you've got lots and lots of practice for the test. These are going to be helpful things to think about as we go into AP chemistry. We discuss how would these potentially react. If I change the way it spins in space, does that change the way it reacts? If I add on other elements instead of, say, oxygen, if I put on a chlorine, would that change things? So it really is the basic foundation for a lot of chemistry to come in AP. So it is very important that you learn this and that you learn it well. Practice, 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 practice is the key. Good luck.